So good morning, children. So this is Playto talk, and this is being happened in a webinar session. So you will not be able to speak back to me, but if you have any questions or doubts, right, you can drop it in the comment box, or if you have a specific question that you want the expert to answer, you can as well use the Q&A section that is in the bottom option, right? So you can use that and you can interact with us. Okay. So hope you children are doing well on this Sunday morning. Yes. Okay. Okay. Great. So for today's session on the Plato talk, so we have our expert, Mr. Shiju Thomas, who is a scientist working at Vikram Sarabhai Space Centre. And I'm super glad and looking forward for this session with Mr. Shiju, where he would share a lot of insights related to the physics of orbiting satellites. And even I have come with specific questions which children's asked in the previous session with another expert. So I would be asking those questions as well along with you and trying to understand how rockets work and how do they function, right? So good morning, Mr. Shiju. You're there?
Good morning, Vasant. Am I audible?
Yes, sir. You're available.
Thank you.
And audible, sir. Yeah. Yes, sir. So how are you doing, sir?
Fine, fine.
Okay, great, great. So we have a lot of kids, waiting to ask some interesting questions to you and learn about space and rockets. Because whenever we interact with kids, space or rockets is one common topic that excites them a lot. So we are looking forward for the today's session, right? So before we begin, sir, wanted to understand from you, like it's not that everyone or not every day you meet a scientist and speak to him, right? So it's a very unique career option that you choose. So can you tell us like where it all started and what inspired you to take a career path in this direction, sir?
Yeah, that's a nice question. First of all, good morning to all the kids and all others listening to this talk. It's very happy to be here. And one thing that we love to do is to interact with the young minds of the country. And I'm happy that I'm getting an opportunity for that. Now, coming to the question asked, as you know, all kids would be interested in the activities happening in the space. Everybody. So I was also interested as a kid and as a student, and while doing my engineering also, I was also interested in all the space activities and especially the activities of ISRO and all. But then, frankly speaking, uh, I doubted my ability to reach there. That is the truth. I always doubted whether I will be able to reach ISRO. Then it happened. Then I had the quest in me. Then when I got the chance to appear for the examination of ISRO, I appeared along with my friends and I passed the test. Then I was called for the interview. Then from there onwards, everything was through. So to be frank, I was a person who was a bit low in confidence initially, but I think more than what I have contributed to ISRO has contributed to me. That's also in fact correct. I gained my confidence and a lot of learning experience from ISRO. So always it's been a passion for to work for the country and to work for ISRO. So I would say I was one of the luckiest person to get into ISRO. I would put it in that way. Thank you.
Okay, okay. That's a very nice answer, sir. I think what you said is very true, right? Like since you had the interest and you wanted to go, the more you think about it, the more you're obsessed about it, the more closer that you get towards the destination or you know, the thought that you have. So really, loved the way that you answered the question. And also wanted to ask you, what is your day like? Because I know how a day of an engineer will be or a software developer will be, but what will be a normal day of a scientist will be? That's a question that I always had in my mind.
Okay, if you see ISRO is not a pure research organization, or it's not like a pure uh, project organization. We do research, but we do research for delivering the products. So we have one way we do research, and it's very interesting part. On the other side, we have a scheduled date to deliver the things. So it's a mix of kinds. It's a mix of, we have to learn new things, we introduce new things to the system. At the same time, we have deadlines. So because we have deadlines, often we will have to extend our work beyond normal office hours, just like any private employer kind of things. Sometimes we will have to work overnight also. For example, last week we had a complete overnight work schedule from night 9 to morning 6 o'clock. So such kinds of things are also there. So in effect, it's interesting but slightly challenging also.
Okay, got it. So it's very dynamic, and you schedule and the work keeps changing on a weekly basis depending on the project that you're working. So I think it's a good thing to know that it's not going to be a monotonous job, and you don't have to repeat the same thing again and again. Good, sir. And also, last time when we met the kids, they were asking about some insights into what is happening inside the space technology, or inside your company or an organization, right? So, any wow moments or any special moments that you had, sir, here at
There
ISRO?
are lot. There are
Mm-hmm.
lot, but I will say one or two.
Mm-hmm.
Especially, the first thing is that when you're developing a system, you'll have a lot of failures. First of all, you will be designing a system based on the knowledge that you have
Mm-hmm.
and based on the understanding that you have. But one problem that we are facing with the systems related to space is that we don't have anybody to follow. We know how we have developed cryogenic technology and all. Nobody gives anything for free. So many times we have to develop things from the scratch. So that put a lot of challenge for us. And while doing that, while developing that, we will be doing with the limited knowledge available with us and improving our knowledge on the way of development, which cost us during the testing. When we test some items for qualifying for integrating to a rocket, we often find that things may not work in the way we designed it. So those are the moments of loss. Sometimes we may tend to lose confidence, but ISRO always had good visionary leaders. So when a person like me grew up, I too had a lot of failures in the testing of the different systems that those were developed by my team. But we always had good leaders and visionaries to guide us what to do and to support us during those moments. So there are a lot of moments of low, but then finally, after completing the entire qualification, and when you put it to a rocket, and when you see that item functioning in a rocket in flight, see a rocket flight lasts barely for 20 minutes. So finally, whatever you have done for last 5 years or 7 years is culminating into a performance in during this 20 minutes. So that 20 minutes is very crucial for us during the launch. So it gives, to witness that launch during the 20 minutes is really a tense moment for any ISRO person. If you have observed their faces during the
So,
live telecast
Mr.
of the
Shiju,
launch.
one second. I think the voice is little low. Can you keep the mic little closer to you?
Yeah, yeah. Is it fine now?
Yeah, that's fine. Yeah.
Okay. So during any launch, it gives us tense moments, and when we come to know that uh, the systems have successfully performed during the launch, that moment really gives us goosebumps. So that is a really satisfying experience that we have during every launch. But we do have failures also, even launch failures also, but that we convert into learning experience. So that's how things goes. There are a lot of lows and there are a lot of ups also.
Got it. Got it. And so I have noted down some questions from kids who had attended the previous talks, especially for this session, because it was a little bit technical, I would say, and kids needed a much simpler explanation from an expert like you. So the first question that I have is, there's a child who asked, how do satellites circle forever? Will they not run out of fuel, or what exactly happens when the satellite enters the space, and how does it revolve forever? That's a
Okay.
question.
To answer the question, as we know, we have artificial satellites as well as natural satellites. For example, if you see moon, shall I show some slides along with it?
Yes, yes, please.
Okay, fine. Is my slides visible?
Yes, it is. Yeah.
Okay, thank you. So as we know, anything we drop fall down. If it is a ball or anything that we drop on the surface of Earth, it falls down to the surface of Earth. That is what we see. And we have moon and we have satellite, everything, but revolving around the Earth and not falling down to Earth. So this is something that we need to understand, how it remains there without falling down to Earth. If you see about moon, it is a natural satellite. That natural satellite keeps on orbiting around the Earth without any additional intervention from any external forces or any external support that we have to see. It has its own drawback also. For example, every year the moon is going far away from Earth by 2.5 centimeter. That's also happening due to the physics of it. Okay. So even without any control, an object can keep on revolving around the Earth. How? That we will answer now. So a satellite is nothing but an artificial body put into an orbit and which remains around the Earth just like the moon remains around the Earth. But the point that we need to see is, a ball, if I drop, it will fall down. But why these objects are not falling down and hitting the Earth? If you see, our Earth is revolving around the sun, but there is a gravity which acts between the Earth and the sun, but the Earth is not falling down to sun. In a similar manner, any orbiting satellite or moon which is revolving around the Earth and which is also acted upon by the gravity of Earth is not falling and hitting down the Earth. So to understand that, we may say this in Newtonian mechanics, we may say this as centrifugal force balancing the gravity, or in theory of relativity we may say it's due to the warping of space-time curve in which objects are following the straight line. Okay, I told you something now, but I'm not going to repeat anything that I told just now because that may get things bit too complicated. So let us try to do some very simple experiments which we all will be able to do and which we all will be able to understand. So let's go to the top of a mountain and just try to throw balls in horizontal direction with a cannon in this direction with a small cannon. First, let us throw it with a very small velocity and see what will happen. So when I throw it with a very small velocity, we all know that it will fall down like this towards the Earth, and that is what it happens. But here we can note one thing, that till it touched the Earth, it was in the air. So it remained in the air for a very minor time, then it touched Earth. So that's what happened. Is my audio coming well, Vasant, now?
Yes, yes.
Okay,
It's
fine.
loud and clear. Yeah,
Okay.
thanks.
So now let's experiment further and let us now throw the ball with some more horizontal velocity. I'm increasing the velocity a bit. So what will happen? We all know how it will go. It will again fall down to Earth, but it will travel some more distance on the horizontal direction. So this is what will happen. So here also the ball, after being thrown, remained in air for some time, then it touched the Earth. So this is what happened. It again fell down to Earth. Eventually it touched the surface of Earth. Now let's continue experimenting and let's go further and throw it with some more velocity in the horizontal direction. So we are throwing it in this direction with some more speed. So what happens? It traveled a bit more distance and it fell down here. And you can observe one thing here, that Earth's surface is curved. So what happens throughout this journey of this ball in this path? So if you see, the ball is starting to curve around the Earth. That's what we observe here. So why does it curve? because when the ball reached the first point, the gravity was like this, because gravity is always pointed towards the center of Earth. So this is one prime reason for why we have the orbits. So gravity is always directed towards the center of Earth. So when ball was at this location, gravity was directed towards this direction. So it started curving towards this direction. Now when the ball reached the second position, the direction of gravity also changed, because it always has to be pointed to the center of Earth. So because of this change in the direction of the force which is acting on the ball started curving around the Earth. Finally, it again reached the surface of Earth at this point. This is what happened when we increase the velocity slightly more. So let us increase the velocity a bit more and see what will happen. So I increase the velocity a bit more, and this is how it would go. And it's obvious, because gravity is always directed towards the center of Earth. So the ball started curving. So the ball started curving. So the but ball had a finite velocity only. So it just circled Earth like this, and it reached at this part of the Earth. This is what happened. So now we can imagine what will happen if you throw the ball at a little bit more higher speed, so that it will always try to fall down towards the Earth, but at some particular velocity it will never be able to reach the surface of Earth, but it will always try to continuously fall down, and it will keep on rotating around the Earth. And this is how actually we get something called circular orbit. If you throw at that right speed from the right altitude in such a way that gravity always attracts it towards the center, and it keeps on falling towards the center of Earth, and it never reaches the surface of Earth. That's how any object remains in its orbit. So this is how we get a circular orbit also. And that's how the moon remains around the Earth, and that's how Earth remains around the sun, and that's how all the planets remains around the orbiting bodies. They are always falling down, but they are never reaching the body. So during this process of falling down, they do not experience any force in between. That's why we say they are all in zero gravity. This you also have experienced in your life. For example, I know you all kids would have jumped from one second or third steps of the staircases to the ground. So during that brief moment, actually till you touch the ground, you are in space and you are experiencing the zero gravity. But don't try to experiment this with too much height. It's very accidental, so don't do that. But whenever you jump up, till the point that you make the contact with Earth again, you are actually in space. You are falling down, but the satellites and these orbiting bodies keep on falling down, and they never reach the surface. That's how they remain in orbit. So if we just a bit more to add to this orbit, so how we can put something into an orbit? So if you throw something from ground at a speed of 7.9 kilometer per second, not considering the aerodynamic drag or the presence of air, if we neglect the presence of air, and if you throw from ground an object in a horizontal direction at a speed of 7.9 kilometer per second, that object will start orbiting the Earth at ground. This is how the orbits work. This is the physics of the orbit. And just one more thing, what happens if we throw it at a slightly higher speed than required for the circular orbit? Then it reaches an orbit something like this, and this is what we call as a elliptical orbit. This is what we call as an elliptical orbit. So here what we did is, at this particular point there is a speed required for throwing in this direction which corresponds to that of a circular orbit, but we increased the speed slightly higher and we threw the object with higher speed than what is required, which results in an orbit like this, and this is called an elliptical orbit. I think I've tried to answer that question.
Yeah, I think even kids also got good information on the way you explained, and they were all giving comments like, wow, nice. and things like that. So I think now it's very clear for us on how these satellites circle Earth forever and how do they operate. And so before I take up the question that I have, there are a lot of kids, enthusiastic kids who have been asking a lot of questions. So I wanted to take some questions from the current kids who joined with us. So there's a question on what are the propellant oxidizers used in PSLV and GSLV?
Yeah, that's a nice question. Can I know the
Hmm.
grade in which that particular student is studying so that I can answer accordingly? That's why. Is
Uh,
it available to you? No.
yeah, around sixth grade, you can see.
Sixth grade. Okay,
Mm,
fine.
mm,
When we talk about fuels used in a rocket, the ultimate aim for having fuel in a rocket is to produce
mm,
high pressure gas,
mm,
to enable high pressure gas flow through a nozzle. So for this we use different kinds of combination of fuels. So one common type of fuel that we use, what we call as solid fuel. Solid fuel means it's a combination of a fuel and oxidizer baked into a single piece. It looks like a cake. Okay. So in PSLV and GSLV, in the first stage, we have in PSLV in the first stage and all the 6 strap-ons, we have the solid fuel, which is a kind of Al2O3 based preparation. Okay, it is a kind of it is a binded with a binder called HTPB, hydroxyl terminated butadiene. So these are the technical terms of it. Since he has asked it, I am just hinting these things. So it is just made into a cake kind of a thing, which includes this propellant as well as oxidizer into a single element. You just supply some energy to it, it burns and it produces high pressure gas. So such type of solid fuel is used in the first stage of PSLV and all the 6 strap-ons, and then in GSLV the core stage it is used. Now there is altogether another kind of a fuel which we call as a liquid fuel. We have seen petrol and diesel, so this is some kind of thing like that. So we the philosophy of liquid fuel is the usage of the kind of usage, the type of usage of liquid fuel is slightly different. We store the fuel and oxidizer in separate tanks and we bring them together into a combustion chamber for burning, and there we get the fuel burned and combusted and we get a high pressure gas. And when we talk about this liquid fuel itself, there are 2 types of fuel. One we say hypergolic. Hypergolic means when we bring the fuel and oxidizer into contact, they burn by themselves. They do not need any external stimuli or spark plug kind of an initiation to burn it. Those types of fuels are called hypergolic fuel. In ISRO launch vehicle, in the liquid engines, we use hypergolic fuel, which is a combination of we have N2O4 as the oxidizer and UDMH is what we call as the fuel. It has a technical name, you can just search, you'll be able to find out more details about it. So unsymmetrical dimethyl hydrazine, it's kind of a hydrazine based fuel. So these are that is a main liquid fuel that we use in our rocket. So in PSLV second stage and PSLV fourth stage we are using similar fuel, and in GSLV in the 4 strap-ons of the first stage and in the second stage we use this fuel. Then there is another kind of a fuel which we usually call as cryogenic fuel. The name derives from the fact that cryo means something belonging to a very low temperature, less than 0 degrees centigrade, so minus 180 degrees centigrade, etc., something like of that order. So cryogenic fuel means a fuel which is stored at that temperature inside the rocket. So as cryogenic fuel we use hydrogen and oxidizer is oxygen. So we have this cryogenic fuel also used in upper stage of GSLV and upper stage of GSLV Mark III, which we now call as LVM3. So these are the different kinds of fuel that we use in ISRO rocket. So initially I told about PSLV and GSLV. Now if we come about LVM3 launch vehicle, which is, I'll just show you a picture also of that LVM3 to get more clarity. So this is that LVM3 launch vehicle that we see in the left side. So this is the latest rocket and the massive rocket that we have developed and which is put into operational launch now. So here if we see on the right side, we see one strap-on, and left side we see another strap-on. So these two carries solid fuel. These strap-ons carry solid fuel. Just I'll take it to another slide. Okay. So just I'll take it to another slide in which I will be explaining this bit, with bit more clarity. So here, this is the GSLV Mercury rocket, or LVM-3 rocket. So here we, on the sides, right side and left side, we have a solid rocket. And this is a solid fuel, and in the center we have a liquid core stage, in which we have fuel and oxidizer stored in respective tanks and brought into the nozzle for combustion. Above that we have a cryogenic stage, which uses hydrogen and oxygen, hydrogen as fuel and oxygen as oxidizer. So these are the different kinds of fuels, those are used in the rockets.
Okay, got it, sir. Yeah. And there is also a question from Kavish. It's like more of an general question. So he is asking how many rockets till now ISRO has launched.
To be frank, I don't have that count with me now. Sorry, I will get into it later.
Okay.
But we have launched. For example, if I say PSLV, PSLV we have launched around more than 50 rockets. Okay.
Okay.
Because we are now running into C55, C56, that number. So more than rockets we have launched. And then GSLV around 10 to 12. That's what we have launched. GSLV around 10 to 12. And LVM-3, the latest rocket of ISRO and the heaviest rocket of ISRO, we have launched X mission, D1, D2, M1, M2, 5 missions.
5 missions.
X mission we are going to launch in the coming March.
Okay.
This is how roughly the number stands, and there are some other small rockets also which we have launched. For example, SSLV we launched last year, and next week also we are going to launch another SSLV. So that will be the second flight of SSLV. That's for it's a small launch vehicle, small satellite launch vehicle. It's the smallest of the launch vehicle that ISRO has developed. So this is how number stands.
Got it. And there's another child, Arav. So his question is, does the GSLV deploy satellite in geostationary orbit?
That's an interesting question. People often get carried away by the names of the rockets. They cannot be blamed 100% because the name of one rocket is PSLV, which obviously expands as Polar Satellite Launch Vehicle. In the name of another rocket is GSLV, which stands for Geosynchronous Satellite Launch Vehicle or Geostationary Satellite Launch Vehicle. So by this name itself, people get carried away thinking that PSLV can be used only to launch polar satellites and GSLV can be used only to launch geostationary satellites. But that's not true, in fact. We have used PSLV to launch geostationary satellites and GSLV to launch polar satellites also. Just now I explained to you how to put a satellite into an orbit. So our objective is only to put a satellite into an orbit to give it that high velocity at that altitude. So if we just see what a rocket does during the launch, it just goes up. And it tilts and it reaches the required altitude, attain that velocity, and just pushes the satellite with a very small relative velocity into the orbit. That means if we want to launch a satellite into an orbit of 150 kilometer, we just take the rocket to 150 kilometer altitude first. But then we know that if we want the satellite to remain in the 150 kilometer altitude orbit, it has to have a speed of 7.8 kilometer per second. That means the final stage of the rocket also has to reach 7.8 kilometer per second, and then just mildly push the satellite into the orbit. So this is what any rocket does. PSLV also can do this, GSLV also can do this. But the only difference is that if you talk about such an orbit, the capability of PSLV or the mass that PSLV can carry and accelerate to this level and put into an orbit is lesser compared to GSLV. So thus GSLV will be able to launch a heavier satellite, whereas PSLV will not be able to launch that heavy satellite. That is the only difference between the two launch vehicles. By the original intention, original requirement of developing the rocket, we have named it as PSLV and GSLV, but both rockets can be used for launching any satellite. For example, if we think about geostationary satellites, the original orbit of geostationary satellites are in fact of the order of 36,000 kilometer altitude. So this is that slide that I am showing now is that of a polar orbit. So we can see the satellite is revolving over the poles of the Earth. That's why we call it as a polar orbit. So the advantage of this polar orbit is that if we see on the right side figure, we can see if we have a camera on the satellite pointing to the Earth, so we can see the path through which the camera will be able to scan. Since the Earth is revolving around the other axis, so if we put this satellite into a continuous orbit like this, over a period of time, it gets continuous scanning of the entire surface of the Earth. That is the advantage of polar orbit, because the Earth is rotating. So if we adjust this swath of this coverage of the camera from or the sensor from the satellite, we will be able to get a continuous mapping. So this kind of an operation is what we call as remote sensing. We are sensing from the remote area, and for that the best possible orbit is polar orbit. So for this polar orbit, the range of the polar orbit, or we say in other words a low Earth orbit, for a general classification I would say low Earth orbit, ranges from around 250 kilometer to 800 kilometer and all. Different satellites are in different such kind of an orbit. For example, our space station is orbiting at around 325 kilometer orbit average. It varies slightly. So that's about low Earth orbit. PSLV and GSLV can launch satellite to this kind of an orbit. But if PSLV is selected, the mass that we can launch will be something around 500 to 600, but the GSLV will have slightly higher capability. That's the difference. Now let us talk about geostationary orbit. So geostationary orbits, the advantage is that we know that we have a rotation for Earth which completes one complete revolution in 24 hours, right? So if we take a satellite into an altitude of 35,786 kilometer and put into a circular orbit, the time period of that satellite coincides with the time period of revolution of Earth. So what is the result? The resultant is that the satellite always points towards a particular region of the Earth. That means a particular geographical region of Earth will be always able to receive data continuously from the satellite. So that is the result of it. That means these satellites we can use for communication. These are the satellites that we use for cable TV and all, because we put a dish antenna on our terrace and we point and align towards a satellite, but then satellite should not jump from there. Tomorrow also that your dish should be able to see the satellite. That means satellite should always stay statically to that particular dish that you are putting. So this is the importance of this geostationary orbit. And I told you that geostationary orbit is at the altitude of 35,786 kilometer. But now how do we launch such a satellite? Do any rocket, or can any rocket go to that altitude and launch a satellite? No. No rocket goes to an altitude of 36,000 kilometers while launching a satellite. Then what do we do? So for that, the technique that we use it, we just go to an altitude of around 300 or 400 depending upon the mission requirement, and we throw the satellite with a speed higher than what is required for a circular orbit at that altitude. So we know that the satellite will then start orbiting as an elliptical orbit. Okay, we adjust this speed in such a way that this distance technically we call as apogee. This distance is 36,000 kilometer, approximately 36,000 kilometer, 36k kilometer. So this is what we do. So we can adjust this velocity so that we can calculate this velocity so that what would be the altitude at the apogee will be 36,000 kilometer. Now what next? So we have put a satellite which orbit Earth like this. At one point in apogee, it reaches 36,000 kilometers and perigee maybe 300, 400 kilometers. Now, if you just think the physics that is happening here, so here the the satellite has a horizontal velocity like this, but that it is falling down and the relative distance between the Earth and the satellite is reducing. But why does this happen? That happens because at this point, right now, the satellite does not have the velocity required to keep it in a circular orbit like this. That's why it's falling down like that. So what we can do at this point, if we fire a small engine which is kept in the satellite itself and increase the velocity to a required value, so that the orbit is converted into the white one to what we see as the colored one. So this is how we launch a geostationary satellite. So the white one is called a transfer orbit. It's not a final orbit of the satellite, but it's a transfer orbit, whereas the other one is the finally required orbit. So this kind of orbital manipulations often are done with the help of small engines which are available in the satellite itself. So this is how this is basically the difference between polar orbits and geostationary orbits. So we use the same kind of rockets only for launching both, but at the same time, depending upon the mass capability, we use different rockets. That is the answer for it.
Okay, got it, got it. It's very nice that not just answering the question in the talk layer, you also went into the deep and explained about how these satellites function and what are the basic differences behind them, right? I think that's very good, sir. And also there is another question, like what is an ion engine in a rocket? Uh,
Okay, that's a good question.
mhm.
Now, in ISRO rockets, we use only chemical propulsion. We term it as chemical propulsion. Can I know what is the grade of that student?
It's one of our viewer on YouTube, so
Fine, fine,
wouldn't
fine,
guess.
fine. That's fine. That's fine. That's
Mm,
fine.
yeah.
So, generally, what we use is a chemical propulsion. Chemical propulsion means two chemicals are mixed together and they are made to react each other, and they generate an energy during that chemical reaction, and we convert that energy into a high pressurized mass flow and we generate thrust from it. That's how we work it out. Now, so to generate thrust, we need to push something out. To push something out of a rocket, we generate thrust out of it. So now, if we see whether there are any better efficient system to generate thrust, we get an answer like electric propulsion systems compared to chemical propulsion systems. So ion propulsion is one such type of electric propulsion which we use in the satellites. It cannot be used in the rocket. I'll explain to that. From Earth, when we lift a rocket, we know that the mass of our LVM-3 rocket is around 640 tons. Okay, so if we want to lift that rocket from the Earth, we need a thrust of more than that 640 tons into G. So heavy thrust is required or high thrust is required. High thrust can be provided only by chemical propulsion. That's why we use chemical propulsion in the rockets, solid, liquid, etc. Out of which solid gives the highest thrust, liquid then generally lesser thrust than the solid, cryogenic slightly more lesser thrust than the solid. But there is another factor which we have not talked about so far while comparing these engines: the efficiency of the engines. The technical term which depicts or which denotes the efficiency of the engine is something called ISP. Okay, so it's a specific impulse. We say specific impulse. Specific impulse is nothing but the impulse or a constant of force into time, or the total force. We can assume it as a total force over a period of time that can be derived out of 1 kg of fuel. Or suppose you're given a specific amount of fuel, 1 kg of fuel, and you're going to compare fuel in a way that you're going to find out which fuel will give the maximum impulse or the force into time constant. Or you can define it in another way also, thrust given in kg per weight flow rate of the fuel, that way also. So it's basically, it's a term which tells about the efficiency of the system. that you're using in your rocket. The chemical propulsion systems, even though they produce high thrust, they are less efficient compared to some other systems. Whereas electric ion propulsion, where using an electric field and a magnetic field, we will be ionizing certain stored gas, and these ions will be pushed out through the nozzle with very high velocity, so that when something is pushed out, you get a reaction and you go in the opposite direction as a thrust. So when we use such systems, we get higher efficiency. So if we compare the ISP, or the specific impulse values of solid fuel, liquid fuel, cryogenic fuel, and ion-based propulsion, electric propulsion systems, they roughly stand like this. Solid fuels, we get an ISP of 270 seconds. And liquid fuels, we get an ISP of around 300 seconds. And cryogenic fuels, we get an ISP of about 450 seconds. But at the same time, through ion propulsion, we get an ISP of more than 1500 seconds. So that kind of a jump is there. But then why that cannot be used in rockets? That's because ion propulsion cannot produce that much high thrust. Then where we can use it? We can use it in satellites for station keeping purposes and all, or to make sure that satellites is kept in the right orbit always, by adjusting against the perturbations that is coming on the orbit, and maybe pointing the camera, aligning the satellite always to point camera towards a particular location of Earth, or example applications like that. So electric propulsion is very promising, but we will not be able to use it in the launch vehicle, but we will be using it in the satellites for different purposes.
Got it. Got it. So I think there's one question which might be similar or near to this. So like, why do we have solar panels for satellites?
Yeah, that's a good question.
Hmm.
So
Is it relevant to this, or it's a completely off topic, sir?
no, it's okay, that's fine. Solar panel is only for generating energy to the satellite. When satellite is in orbit, some energy requirements are there for the purposes like orienting the satellite cameras into the Earth, and then satellite has to process data. So satellite has computers, satellite has transponders, satellites have receivers. So they have to receive the data from Earth, then they have to process it inside, then the commands they have to interpret, then they have to find answers, and they have to collect data from the space, and those data have to be transmitted back to Earth. So they need transponders. For all these, we need energy. So to carry the energy required for these operations for some next 10 years to 20 years and all will be too costly for us. So what we do is, we keep batteries in the satellite, and we charge these batteries using the solar panels in the satellite when they receive energy from the sun. So using the solar panel, we generate energy from the sun and charge the batteries and use it for the purposes for which energy is required inside the satellite. So solar panel is an inevitable element in any satellite.
Okay, okay, got it, sir, got it. And also, I would take one final question from another student. So Rajgopal, he asked, why when we launch the rocket, we use water or water vapor?
Yeah, that's a good question. That's a good question. I think definitely he has read something more into it, and it's a question of altogether a different kind. Okay.
Okay, okay.
So we all would be riding bikes and all. So when we ride bikes, what is the first thing that we do? We turn the key on, then we do next thing. What is it? We kick. Why do we kick? So we have an engine inside and we have a fuel inside, but we need to give a starting movement, starting push to the piston inside the engine so that it starts moving and it starts sucking the fuel, and combustion process is established, and it goes on like that. So in rocket also we have a lot of fuels, okay, but fuels are stored in the separate tanks. Now if we need to start the combustion of the fuels, especially liquid engines, we do not use water in solid engines. It's only for liquid engines. Okay. Liquid engines and cryogenic engines also to a level. So in a liquid engine, so we have just like a scooter or a bike, two-wheeler, we have engine stored in a fuel stored in a tank, and oxidizer is also stored in another tank. So we have to start this process. So for starting this process, we need some combustion to happen and some fuel to be pumped into the chamber using a pump and enable or start the process. So it's just analogous to this kicking of the bike engine. So for this, we do store some high pressure gases in some gas bottles, and using these gas bottles, we run something called prime movers or turbines, and which will generate kind of a steam and for some initial reaction. So some minimum steam generation is required for running this turbine, and using this turbine, we start pumping the fuel into the engine. So this water that we are using in the stage is basically for the prime moving purpose, to get the engine started. And then there are some other purposes also of operating different valves and all, for which we do not rely completely on the stored fuel. So for these purposes also we are using that. If we see the entire functionality of a rocket, it's not just about going high. A rocket includes almost all the aspects of engineering. It's a device where we are putting all the fields of engineering into a single place.
Okay, got it. So there's another question from Chitrang Mishra. Like, what are the different stages of a rocket, and like how it is?
Yeah, that's fine. That's a good question. So before this, can I just show an animation of one NASA video?
Yes, please. Yeah.
Okay, this is actually, first I will show you this particular animation, and then I will show you how the real staging looks like in a space environment. Okay. So here, this is an animation of a rocket which NASA sent in 2010, where we can see the rocket is sitting.
I think you have to share.
Okay, just 1 minute. Are you able to see it now?
Yes, yeah.
Right. So we have a rocket here which has, we can see a different color in the lower part and a different color in the upper part. That just denotes that the lower part is a different stage and the upper part is a different stage. And top we have a pointed area which we call as a heat shield. So this rocket is made of 1, 2 and stages. So let us see what happens when the rocket goes. So the rocket is going to be launched here. So the first stage is fired up and the rocket is moving up, and once the propellant of the first stage is used up, there is no point in carrying that inert mass further. So we can dump that mass so that we can get higher acceleration out of the remaining thrust generated in the rocket, because acceleration is forced by mass. So when you reduce the mass, you get higher acceleration. So we can see, now we can see that particular stage which is burned up and where the fuel is spent, we are just pushing out, because if we continue carrying this engine, then the total mass of the rocket will be higher. That means the acceleration that we are producing out of the thrust will be lesser. So to get higher acceleration, we have to reduce the mass, because force is equal to mass into acceleration, or acceleration is equal to F by m. So for the same force, if you reduce m, you get a higher acceleration, and higher acceleration generates higher velocity. So whenever we use up the fuel of a particular stage, we reject it or we separate it. So this process of separating the unwanted elements once it is used up is termed as staging in the case of rockets. So here what we see is the separation of the first stage, and then here there is another unwanted element also sitting here, which is this sharpened thing called heat shield. The purpose of a heat shield is actually to protect the satellites sitting inside that when the rocket goes through the atmospheric phase. When the rocket rolls through the atmospheric phase, there will be a lot of air friction generated in the atmosphere, in the rocket. So this can cause high temperature and damage to the sensitive electronics and other equipments in the satellite. So we need to protect those things with a cover. That cover is what we call as a heat shield. Once we cross the atmosphere or we reach an altitude of more than 100 kilometers, we do not want this also. So we can separate this element also, we can shed that weight also, so that we will get higher acceleration out of the available thrust. So Now the first stage is separated, and when we go up still higher, what happens? It's moving up still into the higher altitude, and the second stage is ignited. Now that's what we see after the separation of the first stage. Second stage is ignited, and it's moving up, it's gaining velocity, and at this point what will we see? We see that now it has come out of the atmosphere, it has reached more than 100 kilometers. So heat shield is not required anymore, so heat shields are separated. So these heat shields, you can see the two halves, they are actually made as two halves, and they are connected together while integrating into a rocket, and after they are used, they are separated. So the heat shield is separated. Now the satellite is left with one stage, the rocket is left with one stage and a satellite. Now what happens? That particular stage reaches into the orbital parameters, attains the orbital parameters such as altitude, velocity, etc., and then it just separates the satellite into the space. You will be able to see that. So this is how it is reaching the required altitude, and it is orienting for ejection of the satellite, and then satellite is just separated into the orbit. Once satellite is separated, the stored solar panels are deployed so that it can get the energy from the sun, and then antenna and transponders, they are deployed, and then the different elements or the camera or the sensors will have some caps and covers in the assembled condition. So they are opened, and thus then after this process we will be switching on the devices in the satellite one by one. That's how a satellite works. Now I will just show you. This is one of our ISRO launch vehicle, which is LVM3 M2 mission, which we did in last October. Okay, so here the videos that we are going to see here for the separation are actually the ones captured from the cameras within the rocket. Okay, so the difference will be there. So the videos will not be that much beautiful as you saw in that animation, because there is nobody up there in the space to capture these events. Okay, so these are the events captured from the rocket itself with the inbuilt cameras of the rocket. So first we will see the launch. So first, this is the original video captured from a camera mounted on the ground, and this is a majestic LVM3 M2 vehicle, and it is taking off. So the two solid strap-ons which are on the sides are ignited, and the central liquid engine is still not ignited. The two solid strap-ons are ignited, and after reaching some altitude, the solid strap-ons will be separated. So we will be able to see that particular separation. So right now what we are seeing is the view from the camera of the rocket. So imagine that in this center portion there is a big cylinder that we are not seeing now. Right side what we see here is the strap-on one side, and left side what we see is the strap-on on the other side. And in the center we have this much big stage which we are not seeing here, which is just trimmed to make this part of the video clear. So we had two cameras kept on it, and you can see just it's moving up. This is the view that we get from there, and just see what happens now. So once these solid stages are burned, these solid stages will be separated from the rocket. You can see that's how it is. I'll replay it once again. So these solid stages will be separated from the rocket, and this is how it is viewed from a rocket. You can see the solid stage just were separated and they fell down. And further we are continuing with the flight, and now we see these are the satellites. So you can see total 36 satellites were there in this mission, and we can see something, a small right one separating here. That is one of the satellite that's getting separated. You can see into the space, and the other side also you can see, since the orbital conditions there did not have enough light, we have slight visibility problems in this camera, but for some other separations we have good visibility for the satellite. You can see the satellites are getting separated. So these are views from the camera in the launch vehicle itself. Now I'll show you one more video related to this. So this is that of a PSLV C-54 mission. Here the lifting off and all, takeoff and all, there is not much difference. But one thing that I wanted to show you was the onboard view of the separation of the heat shield. Okay, just see here. So these are views from the onboard camera, and what we see here is the separation of heat shield into two halves. So initially what we see is camera is mounted on the two sides of the rocket, and they are facing the inside part of the heat shield. Now when it separates, the two halves are separating like this. So this is a live video, not live video, this is a recorded video of from an onboard camera where we can see the heat shield separating. And this is how the satellite, that particular mission had a main satellite in the center, and this is how that main satellite is separating into the space. And this is another small satellite which is called Thibault, and it had some another satellites also called Astrocast. Also it had multiple satellites. So these are all how the other satellite separates. So this is how staging works. In fact, staging is an essential part of the rocket, where we make rocket into different stages, and once the operation of that particular stage is completed, we separate that part from the rocket. That's called staging. And for satellite also we need to separate. Okay.
Got it. I think it was a very nice demonstration with the animation and the video, where it was pretty clear how it works and what exactly happens after a rocket is launched. So very insightful, sir. Thanks for that. And this is another child, Nerky, who have asked a couple of questions in YouTube. So we all know about SpaceX. So what do you think about them? Like, why are they so fast? Or what's happening with them? And can we expect more such companies to come up like them? Is a question which he has asked.
Okay.
Mm,
It's a good question. At the same time, it's a tricky question also.
mm,
Okay.
mm,
Uh, First of all, I will make a brief comparison between ISRO and SpaceX.
mm,
Okay. As you know, ISRO is a governmental organization, whereas SpaceX is a private sector organization. So there,
right.
obviously, the decision making, everything will be so fast. And SpaceX is a wonderful company which is doing wonders in terms of many technological advances and innovations and etc. There is no hiding from that. At the same time, they have a better, easy, fast decision making process which helps them, enables them to put things under series in a fast pace and all. So in India also now we are starting such an ecosystem. A lot of private companies have started shaping up, and soon, with the support of ISRO, we hope a lot of private companies will be, which are with a lot of private companies which are built up in India will start competing companies like SpaceX. It's too tough, but we do think it will happen. And taking nothing away from them, SpaceX is a wonderful company which is leading the world in many technologies related to this rocketry and all. But certain points to just to bring to your notice that, do you know SpaceX has only one type of engine? They have only a semi-cryo engine. They do not have a solid engine. They do not have a liquid engine, because their requirement is what they decide. Their requirement is not something that is coming from outside. So they have decided to make one engine and to produce it just like a car manufacturing company. You know, if I'm producing only Maruti cars, I know how many parts I have. So these parts can come at a very high pace from a manufacturing unit if you are producing it in bulk. So that's a kind of a way in which they are doing, and they're doing a lot of innovations in that, and they're doing a lot of they are, in one sense, the leader of the SpaceX has a lot of ambitious plans which may lead the space activities, entire space activities in the world, to an altogether another level. We have to wait for that and see. And they have already implemented a lot of advanced technologies like taking back or retrieving the stages once they are separated. Those are all breathtaking technologies. Those have been incorporated into this space sector. So those are very good, and we look forward to that. And I'm sure, and we are sure that in India also a lot of startups now have evolved, and they will also come up to that level. So one day we will start talking about those companies also incomparable with the SpaceX. So let's hope for that.
Right. I think very soon we would be seeing the space revolution, where a lot of companies and people start working towards the direction. And on a general note, so children, we did have the webinar last week where someone from a space tech startup came on board and explained about the future scope and the career opportunities in space tech for kids of today. So I would share that link as well. Please go through it. And if you have subscribed to our channel, YouTube channel, you can also see the video over there and get some insights into it, more information. And coming back, want to ask, what are the future projects? Like, what are the projects that you're currently working on, and how does it look, sir?
Okay, I'll just share the screen once more.
Sure, sir. Yeah.
So right now ISRO has in fact developed this many launch vehicles. We had SLV-3 and ASLV, which were just experimental launch vehicle, which would enable us to make commercial launch vehicle. And PSLV we have in fact developed and we are launching right now also for commercial missions. And we have GSLV Mark II and we have LVM3 called as GSLV Mark III also. And then this is the on the left side, what you see is small satellite launch vehicle, which is the newest launch vehicle that ISRO has developed. And we're going to launch the second development flight of this particular rocket in the next week, probably February 8 to 10, that time frame. So this is one rocket that we have developed. This is for carrying small satellites. And another ambitious mission, I'm talking about only the major missions. Okay, there are a lot of minor missions also, which I'll just mention in the end. So, and another major mission that we are going to do about that we are developing on the way is Gaganyaan mission, in which we will have a crew module put into a rocket called Human Rated Launch Vehicle, and which will orbit the Earth, and which should safely come back also. So that is the Gaganyaan mission, for which we are going to do a lot of tests using a small rocket called a test vehicle. Using the test vehicle, we will be demonstrating different phases of the missions of Gaganyaan. So these are the SSLV is almost developed, and Gaganyaan mission is one of the mission which is undergoing development in ISRO with very high impetus. And then we have small missions like reusable launch vehicle demonstration, which is also one controlled landing of reusable launch vehicle is going to be demonstrated within 2 weeks from now at a place called Chitradurga. That's also being planned. A lot of such, then there is something related to air breathing propulsion technology that also we are going to demonstrate soon. So those are some of the missions those are coming up, but the most important mission that is undergoing development in ISRO is the Gaganyaan mission.
Okay. Very insightful, sir. And you did mention about a few other missions that you would like to inform. Just what are those? So can you share some light on that, sir?
Those were this RLV, reusable launch vehicle missions that I mentioned, and then DMRJ, etc. Those kind of things.
Okay.
Then apart from this, we are talking only about rockets, but apart from this, ISRO is doing a lot of other things also, which we generally call as spin-off.
Okay.
Spin-off means we will be developing some technology for injecting those into the rockets. But this technology will have a lot of applications elsewhere also. For example, a particular material which can withstand very high temperature or very high stresses or something like that, a special plastic material which can be implanted into an artificial valve, kind of a thing. So those technologies are what we call as spin-offs. So ISRO has a lot of spin-offs also. So recently we have spearheaded development of lithium-ion technology, lithium-ion battery technology. So those kind of things are also there. Those are small things which goes into the part of development of rockets, but which will have some other applications outside also.
Okay. Got it. And so there's some questions related to science. So in general, if kids want to get started with the space science, the concepts related to space, right? So where they have to start, like what is that, they have to focus more on?
Okay, I need a bit more clarity on that question. Is it related to a career option or generic interest?
Generic interest.
Fine.
Mm,
Uh, you kids are more blessed than us. When we grew up, we did not have a platform like YouTube or online videos for learning like what you're doing now. So you have, and I know you almost all kids. I too have kids. Would be very fond of this digital platforms and use of internet and all. So today, if somebody asks me how you can grasp more and more things related to space, it's nothing else but from internet only. But use your time productively and watch some creative YouTube channels like that of Playto Labs and all. There will be a lot of other channels also. So just understand things and don't limit reading to one source. That may confuse you. The primary quest that you need to have in you is to ask the question why, not to anybody else, but to you yourself. You're seeing one thing. You just try to understand how it works, what makes it behave that way. And since rocket is almost concerned with physics, I'm almost sure that you will be able to understand it in physical terms, except the quantum mechanics part of the physics. If you go to quantum mechanics part of the physics, yes, you will not be able to understand anything from here on. You will have to believe a lot of things that has come out of experiments. That's fine. But other than that, all the other technologies related to physics or the other findings related to physics, you will be able to answer based on your own questions. So the first thing is question yourself and try to find the answer for that question from multiple sources in the internet or from anywhere. So this quest of keeping asking questions to yourself will definitely improve you. Unless you develop the habit of asking questions to yourself, the development may not be possible. You keep on pestering all the elders with questions, so they also let them improve. They will improve and they will try to find answers for you, and you will also get benefited. So keep on doing that. That's my take on that.
Okay, got it. And there is also another question on like this was answered by the previous expert as well. But since you are also a senior expert in this field, wanted to ask you, like for a career perspective, right? If they want to get into space or if they want to start working related to space technology, as you said, it's going to boom. A lot of companies are going to come, right? So what are the subjects or what are the things that they have to really have a strong foundation so that it would be helpful for themselves?
That's a nice question.
Mm,
When we talk about rockets and space, people may think we are seeing only the rocket moving up and some gases coming out of it.
mm,
But is it only about that? No, it's a rocket is a culmination of all engineering applications, to be frank. So right from a metallurgist who design a material to be injected into a rocket, and a fabrication expert whose expertise is to fabricate things to give final shape to a part of a rocket, and then an integration expert who just try to find out where the joints can be put and how the different parts can be joined, things like that. Then a computer expert who can work out a programs for guiding the rocket. So a mission simulation analyst who can analyze or predict the path of the rocket under certain conditions. So a rocketry is inclusive of all of this. To develop a rocket, you need expertise in all of this. Definitely it's not possible for a single person to develop expertise for this. So what I mean to say is, if you become an expert in any one of these subjects, you will be able to contribute into the space related activities. So the kind of uh, expertise that generally people are looking forward is gain very good expertise in one subject. It can be any of this that I told. It can be core engineering, core structures, dynamics, or any of the things, structures, dynamics, or computers, or algorithm development, mission control, control guidance. A lot of things are there: fabrication, material, then fluid dynamics, gas dynamics, a lot of areas are there. In ISRO, we have experts in all these areas, contributing together, working as a team for a final goal, and develop expertise in this one area, and develop some working level knowledge in all other fields. That is what is required, so that you will be able to understand when you are working as a team the concerns of the other experts, of the experts in other area, and you will be able to solve their problems using your expertise in your area. That's how a good teamwork goes. So you need not to become an expert in a particular area, but in the field you are working, in this vast kind of engineering field, we have to build expertise. So that expertise can be used in realizing or developing a rocket.
Got it. Got it. Got it. So, yes, children, I think you got good answers from Sir on space technology and the physics of orbiting satellites. And few kids did leave the session because they have a class at this time. So, other children, so whatever questions you have, please you can ask to Plato teachers in your class. So they would try to answer it, or they would get it answered from an expert. And also, please, everyone, subscribe to our YouTube channel, Plato Labs YouTube channel, so you get more insightful videos such as this. And you can also get good information on what's happening and what's going to be the future. So please stay tuned to our channel. And also, those who watch this session at YouTube, I'm sure you had a lot of questions. Still, we have around 50 questions which kids have asked. So, students, you can ask the Plato teachers in the class, and they will get answered. And for others in the YouTube, you can also drop your questions as comments there. And I have also noted down all your questions. So we would be giving you the answers in the comment box. Unfortunately, we couldn't have this session for a longer period of time. We wanted to, cut short it so that it's very effective, and others are also having a lot of engagement right now. So I have noted down all your questions. So we'll make sure that we are putting out the answers in the YouTube video itself as comments. So please do check it out. And once it is updated, we would also be getting a notification regarding this. So, yes, sir, Mr. Shiju. So, on final words, like, what do you want to say to these kids, who have asked a lot of questions which I'm not aware of, not heard of as well, right? So,
Yeah, I was
what do
just going through the going through the QA session. So are there white holes? Okay, white holes theoretically exist, but not proven so far. Are there all what at altitude does the solid boosters of GSLV detach? Okay, it's around 50 to 60 kilometer altitude. So first of all, GSLV does not have a solid booster, so that's a correct. There is a rush in that question. So there are some questions about Mr. Nambinara, and also sorry, I am unable to answer that. Okay, so can we use ammonium perchlorate? Yes, sure, definitely. So there are a lot of questions. So seeing these questions, I can understand the enthusiasm that the kids are having, and I hope that India's future is bright.
Yes, sir. Yeah, even we believe in that, and I'm sure that kids are getting started at an early age. And as you said, if they focus on one specific subject, and if they focus on a goal, and if they start working towards it, right, and become an expert at that particular direction, definitely they would be on the path to succeed. So I think that is a very good thought, and we would take it forward and make sure that we help kids in whatever ways possible to ensure that they are going into a successful future. Yeah. So once again, it's really wonderful having you here, sir, for this talk. Hope we didn't disturb you on the day off. I understand you are very busy with a lot of things, but really thanks for joining at this time and sharing some insightful information to us. I'm sure that it inspired a lot of kids over there, and it's going to inspire a lot more as well. So thank you, sir. Thank you so much, sir, for joining this.
Happy to be part of this. Thank you for the invitation.
Mhm.
So loud the session. Thank you.
Yeah, thank you, sir. Yeah. So children, so as communicated, so this video would also be available in our YouTube channel. Please subscribe to our channel so that you can get the notifications regarding this. And if you have missed the previous week webinars on the future of space tech for today's kids, it is also available. So please do check it out. And if you have some questions, please do drop us a comment in the YouTube. and we would get it answered through an expert and reply to it as soon as possible, right? So until then, it's bye bye from my side. So we would meet you in another Plato talk with an expert who would guide you on some interesting topics. So do watch out for the invitation in your WhatsApp and email, and subscribe it immediately so that you get to participate in the discussion. Okay. So bye bye everyone. So have a great Sunday today.